The KF-21 program has always been presented as more than a new fighter entering service. For South Korea, it represents a benchmark of industrial maturity, a test of whether the country can move from being an advanced defense manufacturer to becoming a truly autonomous aerospace power. Public debate often focuses on speed, stealth shaping, or how the aircraft compares to American or European fighters. Yet for a Korean audience, the deeper question is more strategic. Can the KF-21 be considered a national combat aircraft if its most critical component, the engine, remains outside Korean technological control? At present, the KF-21 relies on engines developed by GE Aerospace, a proven and reliable solution that allows the aircraft to enter service on schedule. Korean industry, led by Hanwha Aerospace, participates through licensed production, local assembly, and maintenance infrastructure. This arrangement has clear benefits. It reduces development risk, ensures predictable performance, and builds an industrial ecosystem around assembly, testing, and lifecycle support. However, it is important to be precise in how this is described. This is industrial localization, not technological sovereignty. Core design authority over the hot section, digital engine control software, and advanced materials remains external. For an aircraft intended to anchor the Republic of Korea Air Force for decades, this distinction matters. Fighter engines are not interchangeable components. They define upgrade ceilings, dictate how much electrical power can be extracted for sensors and electronic warfare, and ultimately determine how freely an aircraft can evolve. Dependence on an external engine supplier means that every major modernization step is influenced by foreign export controls, certification timelines, and political considerations. From a national perspective, this is not a criticism of current partners, but a recognition of structural reality. This is why Seoul's decision to pursue a domestically developed fighter engine is strategically significant. The issue is often misunderstood as a simple competition over raw thrust numbers. Media headlines tend to fixate on figures such as 16,000 pound force or comparisons with higher rated engines. For a technically literate audience, it is essential to clarify that thrust ratings depend on configuration, operating regime, and measurement standards. Dry thrust, maximum afterburning thrust, and growth margins are not directly comparable without context. More importantly, thrust alone does not define strategic value. What South Korea is attempting is not to immediately outperform established engines, but to master the full cycle of design, testing, certification, and iterative improvement. This shift transforms the engine from a purchased product into a national capability. Once that transition is made, performance growth becomes an internal decision rather than an external negotiation. For a country that has already demonstrated world-class competence in shipbuilding, semiconductors, and precision manufacturing, this step is a natural, if difficult, progression. The true challenges lie in areas that are invisible to most observers. The heart of any modern turbofan is the hot section. Developing turbine blades capable of operating at extreme temperatures requires mastery of single crystal alloys, advanced ceramic thermal barrier coatings, and tightly controlled manufacturing processes. These are not problems that can be solved quickly through incremental investment. They require long-term accumulation of data, failures, and redesigns. Similarly, high-pressure compressors demand sophisticated aerodynamic modeling to balance efficiency, stability, and durability across the entire flight envelope. Equally critical is the digital engine control system. Modern engines rely on full-authority digital engine control software to manage performance, protect against faults, and integrate seamlessly with aircraft avionics. Writing this software, validating it under all conditions, and certifying it to military standards is a task as complex as the mechanical design itself. Beyond that comes testing. Endurance trials, foreign object ingestion, icing, electromagnetic compatibility, and vibration testing consume years and substantial resources. For many programs, testing rather than design becomes the primary schedule driver. These technical hurdles highlight why a domestic engine program cannot be treated as a single company initiative. It is inherently national in scope. Materials suppliers, machine tool manufacturers, software developers, and research institutes must all advance together. In this sense, the engine effort is as much an industrial policy project as it is a defense one. For Korean audiences, this framing is important because it connects defense investment with broader economic and technological resilience. Looking ahead, the implications for the KF-21 itself are profound. Future iterations of the aircraft, particularly the planned Block 3 configuration, are expected to emphasize deeper sensor fusion, expanded electronic warfare capability, and reduced detectability. All of these trends increase demand for electrical power and thermal management. An engine designed with Korean operational concepts in mind can prioritize these needs from the outset. It also allows more flexible adaptation as threat environments evolve without waiting for external approval or redesign cycles. Export considerations further strengthen the case. As Korean defense exports expand, potential customers increasingly seek not just equipment, but long-term partnership. An aircraft powered by a domestically controlled engine offers Seoul greater freedom in negotiating export terms, maintenance arrangements, and technology transfer. For buyers wary of dependence on multiple foreign governments, a more sovereign Korean platform can be attractive. This does not mean abandoning alliances, but rather entering export markets with greater confidence and autonomy. Beyond the KF-21, the strategic logic extends into the next decade. A mature fighter engine capability becomes a foundation for unmanned combat aircraft, dedicated electronic warfare platforms, and eventually future generation fighters. It also feeds back into civilian aerospace, materials science, and high-value manufacturing. In this sense, the engine program is not a narrow military project, but an investment in national technological depth. For South Korea, success does not require producing the most powerful engine in the world on the first attempt. It requires establishing control over the process by which power, efficiency, and reliability are improved over time. The KF-21 does not need to surpass every foreign competitor to fulfill its strategic role. What matters more is that its evolution is guided by Korean priorities, Korean timelines, and Korean industrial judgment. When viewed through this lens, the importance of a Korean-made fighter engine becomes clear. It is not about prestige or symbolism alone. It is about ensuring that a flagship national defense program remains fully under national control throughout its service life. In the 21st century, sovereignty in advanced air power is measured less by airframe shape than by mastery of the technologies that sustain and evolve it. For the KF-21, the engine is the final and most demanding step on that path.